So let's consider inductance of a circuit. So first of all, we need to make sure that we understand there is a difference between an induced EMF and a direct current potential difference, like from a battery. Our induced EMF is going to be due to a change in the magnetic flux over time. I'll just put an absolute value sign around that so that we're not really concerned at this point with the direction of that potential difference. So if we consider this simple circuit where we have a switch that we can close and a voltage source, a DC battery, the current would flow from the positive side, the conventional current would flow from the positive side of our battery through our circuit and back to the negative side of the battery. And in doing this, a magnetic field will be induced around the wire. So if the current is moving in this direction here, then the magnetic field, put your thumb in the direction of the current, grab the wires. So you would have magnetic field going into the page here, coming out of the page there, and so we would have magnetic field kind of looping around this wire here. And previously there was no magnetic field inside this area. There was no magnetic field here. So now we have a case where we have a changing magnetic flux in the area of inside the physical structure of our circuit. This induced EMF due to the current directly proportional to the change in the current. So because a current is changing, we get a magnetic flux, and then there is a L, which is our inductance constant. This inductance depends on the geometry of the loop. So Faraday's law tells us that this EMF would be equal to negative, remember the negative sign, n number of turns times our d phi dt. So let's set that equal to this side, so equals negative L, the inductance, di dt. Now if we integrate both sides here, we'll get that n phi is equal to L times the current. So then our inductance is equal to the number of loops times the magnetic flux divided by the current. So our inductance is going to depend on the geometry, the number of loops, and the magnetic flux through that loop, and then the current that is passing through the loop. So inductance is measured in Henry. Our number of loops is just a number. The magnetic flux is in Tesla times meter squared. Remember, flux is BA cos theta, and a Tesla meter squared is also known as a Weber, or WB, and then the current would be measured in amps. So this inductance is the measure of the opposition to a change in current.